Thank you very much for joining us over here. Started just a moment earlier. We were going to show the screen, but I guess we decided to kick it off here, which is perfectly fine. So we want to welcome you here to our webinar. You are certainly in the right place if you are here for our webinar for what constitutes high-speed design. Our presenter today is Sean Kelly, who is our resident expert in high-speed design. Now, before I do turn the mic over to Sean, I want to encourage you to write questions in the questions panel that is found in the GoToWebinar panel that should be up on your screen. If you don't see it, then press that little orange arrow and it should expand it out. Of course, if you want to close it, you can press that arrow again and it will compress it down for you. But please do be specific with your questions, and Sean will have definitely some time to answer those questions in the end over here. So we're just going to give Sean here just a moment to pull up his screen.
Well, thank you, everybody, for joining me today in this webinar on how to know if your circuit qualifies as high speed. So before we get started, I want to identify the purpose of this webinar. Mainly, I'm going to be using this to help those of you who have little background in high-speed design, or those of you who have some experience to get a second opinion. I'm going to give practical understanding of what constitutes high-speed design in order to create a baseline of understanding. I'm also going to explain why high-speed design changes the approach needed by the designer and the person doing the PCB layout. So as I go through today's lesson, we're going to talk about the schematic portion, the component selection, and then on the back half, we're going to actually talk about the PCB layout aspects. I'm also going to give some solutions relative to high-speed designs. Now, if you're interested in learning any more after this presentation, we have quite a few different webinars on this same type of material that are similar. Just reach out to us at support@9.connex.com and we'll get that out to you. Specifically, you want to look for Enough with High-Speed Theory Already series that I did a couple months ago. So now the question that I pose opening this webinar with, why is it important? It's important because EMI is a problem for quite a few people. And if you're not familiar with the term electromagnetic interference and you're new to design, you'll learn real quick what EMI is. But there's EMI for compliance testing. There's also EMI for general compatibility within your own product. But there's also problems that people have with crosstalk between signals on the board. If you have a receiver in your product, you need to be aware how high-speed designs can affect the noise floor. And if it's high-speed design, you have to be aware of that because there's different aspects on signal propagation. So I want to identify one thing. We're not here to make you all FCC certification experts, but it is important for you to understand where we're going and why we're going that way. And one of the things I want to talk about is the FCC certification for a product to make sure that it is compatible in today's life, and no matter what the situation is. And the FCC will establish limits on what frequencies and power can be allowed to radiate from a product. One of the main concerns of your design is how frequency content will be tested in order to stay within those FCC limits. Now, oddly enough, for most of us, we realize that 9 kilohertz is a very low frequency, yet the FCC defines any digital device as one that generates or uses digital timing signals greater than 9 kilohertz. Now, in order to prevent radio noise generated by your digital device that you're designing from interfering with any radio communications, digital devices must be designed to contain that noise, aka your high frequency content. And it does so in two different ways. The first way we're going to talk about is called limiting your radiated emissions. And you can control the radiation by one of two manners. You can either design the digital circuitry in a manner that minimizes any radio noise emissions, and if you can't do that sufficiently, then you will have to enclose that circuitry in a manner that prevents that radio noise from escaping. And that's really a key to passing EMI testing, is trying to keep that signal from escaping. We're going to talk a little bit more about that in a little while, but it has to relate to things on your board acting like an antenna. The second way is limiting conductive emissions. That is, we want to make sure that any of the signals being generated on our product don't go out the power line and get put into the power system. So you'll typically include a well-filtered power supply that'll keep that noise from leaking out on the power lines. Now, devices are fall into one of two categories, Class A and Class B. Class B is really, let's back up for a second. So the class is really geared toward the concept of environment. So when you hear people talk about a class of product, think environment. A Class B device are those devices that are marketed for use anywhere, including residential environments and by anyone in the general public. Let's say you have a TV remote. You want to make sure it plays well with other devices in your house, your phone, a watch. Perfect examples. Class A devices is an environment that's geared toward business application and industrial environments, such as a switch. And here's a commercial grade ultrasonic cleaner. These devices are not going to be in the general public. They're not typically going to be in a residential area. So the requirements for Class A devices is actually less stringent. Now, the FCC is going to require that tests be performed on your device to make sure that it plays well with others. These tests or verifications are going to measure the levels of radio frequency energy that are radiated by the device into the open air or conducted by the device onto the power lines. After these tests are performed, a report must be produced showing the test procedure, the test results, and some additional information about the device, including design drawings. Now, this specific information that's put in a report is detailed in Part 2 of the FCC rules. You as a manufacturer are going to have to keep a copy of this on file. Now the FCC even allows you to self-declare to allow you to get to market faster. Now, Part 15 is subdivided into two sections based upon radiators that are either intentional or unintentional. Subpart B is for the unintentional radiators. In other words, that's a product like your watch that we showed before that's not supposed to be transmitting or receiving information outside of the product. These are devices that contain clocks and oscillators, but that they do not deliberately generate these radio frequencies. The two levels of radiation and conducted emission limits for unintentional radiators are specified in that subpart B. Subpart C is for intentional radiators, such as your phone or the TV remote. In any case, intentional radiators must have a permanently attached antenna or provide a unique coupler to prevent the use of unauthorized antennas. Again, the concept is the FCC wants to make sure that your product doesn't put out too much energy out into the normal space to affect the ability of other products to work properly. Subpart C rules for operation of radio transmitters, for the most part, are very detailed regarding fundamental field strength, power and or power density, frequency accuracy, and permitted harmonic and spurious emissions. And what you'll see now is a table. If you notice on the left-hand side, Part 15, Section 107 talks about the conducted limits based upon the classification of your product, whether it be B or A. Notice that the conducted limits is limited to an upper frequency of 30 megahertz. Section 109 talks about the radiated emissions. Notice it starts at 30 megahertz and goes all the way up in steps to 960 and above. The one thing I want you to notice here is that Class A devices are tested at 10 meters, where Class B are tested at 3 meters. So in other words, the signal that's going to be a Class B is automatically going to be stronger because it's closer. It's called an inverse square law. But also notice that even though there are different distances, this particular section 88 to 216 has the same rating, 43.5. Now, as you notice, these numbers get bigger. And what that means is your system, a product, can actually radiate more of this frequency than it could at lower frequencies. And what you'll find out later on when we talk about antenna concepts is that the smaller the frequency wavelength is, the easier it is to escape your product. Now here's a graph showing the relative weights of that test. The Class A product is in orange, and then Class B is in the green, dark green. Now, the interesting thing, if you've not done this before on your product, FCC can issue penalties to a person or company that sell a non-compliant digital device. And the reason why I put this on here is it can be quite motivating to you to take all this into consideration. The fines can be up to $10,000 per day per violation. Pretty stiff. So one of the reasons why you want to ask the question on the beginning of your design is this a high-speed design? Because when it is a high-speed design, there is a greater probability that you're going to fail this test. And if you don't go through the design requirements to make sure that you pass the test, this is what you'll have to deal with. So the first polling question that we have is, if you don't mind, I'd like to ask you the following question. About what frequency band does the FCC make the radiation emissions limit the same regardless of the class of device? And by the way, if you're new to this type of system, all you got to do is make your selection, and I give you about 10 seconds or so to make your selection. Okay, looks like the majority of you all are paying attention. That's awesome. C is the correct answer. Now, here's the thing that to me was very tricky when trying to explain to people this concept. Remember I brought up the fact that Class A was at 10 meters and Class B was at 3 meters? If you were actually to compare the same distance, what this chart actually shows is that for Class A devices, here is the sensitivity of that signal. Notice, it's very high. The electric field can be quite strong compared to a Class B device. This is when you're measuring at the same distance for both products, regardless of what the class is. This gives you a better appreciation for how less stringent Class A, that is industrial type of devices, can radiate and still pass. Now, why did we go through all this? It's because I want you to understand the frequencies that the FCC is concerned about, specifically the band at 216 and up. I wanted you to understand why they're tested, under what conditions they're testing it, and then the type of products. The next step is to understand where these frequencies come from. So polling question number 2. What do you think constitutes high-speed design? Okay, so it looks like 45% got depends, which is actually the correct answer, and I'll explain here in just a second. On D, 16% of you all said 1 nanosecond, and that is a very common rule of thumb, and definitely A and B would be considered high speed. The interesting thing is C could be, depending upon the situation. So with the answer being it depends, we have to understand that the actual answer, you need to look at 2 ways of understanding the answer, and that is, are you going to look at it in relationship to harmonic content or the rise time of the signal? If the signal's fundamental frequency is 300 megahertz, then automatically there are going to be a higher order harmonics to be concerned about. And if that doesn't make sense automatically to you, bear with me, this will make sense later on in the presentation. A low frequency with a fast rise time can be considered high speed. And that general rule to follow is that if the rise time is faster than 1 nanosecond, then there are definitely high frequencies to be concerned about. Now let's review harmonic contribution. This is a part that I've covered in a previous webinar, and I've scaled it down because it's really important that you understand this portion as we move forward. We're going to define the harmonic contribution of a square wave. Now I understand that you're not typically going to be looking at square waves. They're going to be asynchronous shapes, but to help understand the concept of what the harmonic contribution is, it's easier if I explain it with a square wave. Now, when I first got into electronics many years ago, I really didn't understand the frequency domain. I was using an oscilloscope all the time, and so I understood the time domain concept. But it wasn't until I took EE classes to get my engineering degree that I understood that time domain signals had a corresponding frequency domain. And what that basically means in a nutshell is when you watch the voltage change in time, it does so because there exist specific frequencies with specific power all at the same time in the circuit. It's called a concept called superposition. So when you're looking at a square wave, this blue is the ideal square wave, then the actual square wave is going to be more like what you see in red. But it can only happen like this in time because in the frequency domain, you actually have multiple different frequencies. So you're going to have the fundamental of that square wave. That's what you see here, and the black is 100%. Then you also have the odd harmonics. So this would be third harmonic, fifth harmonic, so forth and so on, in these relative weighting of the signal strength. And you can see here's the third harmonic, so here's 3 waves all within the same base period. Now, why do we have all those signals? We do so because there's a mathematical equation that can help us understand exactly what makes up that time domain signal. When it's expanded out, by the way, it's called a Fourier series, and don't faint when you see this because the object of my webinars is not to confuse you with a whole bunch of complex mathematics. I want you to understand the basics of concepts. But when you're looking at this equation, you can break it down into, there's a multiplier out here, but then inside the parentheses, you have specific terms. Here's the first term, here's the second term, here's the third term. This first term, the 2 pi f, that's the fundamental frequency. So in other words, if you're looking at 1 kilohertz square wave, you're going to have 1 kilohertz as your fundamental frequency. The second harmonic, which is the third harmonic, that's the 6 pi f term. That's the second term in there. So again, if you had 1 kilohertz as your fundamental, then you're going to have 3 kilohertz also. The third term, the 10 pi f, that's here. That's your fifth harmonic. And so on. But for all intents and purposes in the real world, anything past the 7th harmonic is not typically relevant. We don't have any even harmonics because the sign of 0 equals 0. So that'll play more into the discussion as I show you an applet. Now this applet, I don't want you to go to it right now, but it is really fun to play with because you can look at all kinds of different wave shapes and see what frequencies in their phases are making up that time-based waveform. But I'm going to use it to demonstrate something. And again, the first thing I want you to understand is that the frequency of the square wave is not what's important in this demonstration. It is the relationship between the spectral content and the fundamental frequency of the discussion is always the same. So in other words, if my fundamental square wave is at 1 kilohertz, then I'm going to look at 3 kilohertz and 5 kilohertz. If my fundamental is 5 megahertz, then the third harmonic is 3 times the fundamental, and the fifth harmonic is 5 times the fundamental, and so forth and so on. It doesn't matter what the fundamental square wave is. The third harmonic is 3 times, and the fifth harmonic is 5 times. Mathematically, every perfect square wave is composed of this fundamental frequency and the odd harmonics of it in descending power levels. Now let's take a closer look at the applet while keeping the superposition concept in mind. Using the default number of terms and the default magnitude of each harmonic, you can see a really nice square wave. Notice that the steepness of the rise and fall is definitely there, and you have the little Gibbs effect there at the leading edge and the trailing edge. Also notice that all the even harmonics are equal to 0. So here's your fundamental. There's a second, there's a third, there's the fourth, there's the fifth. So you see that there is a decreasing level of all the odd harmonics. Now, if I reduce the number of those harmonics and I start limiting those upper ones, you can notice now that I've gotten rid of all this up here. The net effect is now my square wave that looks so close to perfect has got a lot of ripple in it. The effect of what you see is what happens when you pass this signal through a low pass filter. Also notice, and this is very important, notice how the slew rate has decreased. So in other words, this nice steep waveform that you saw here with all the odd harmonics now is much slower when you're removing those higher harmonic signals. If the fundamental frequency was 1 gigahertz, then we are looking at up to 9 gigahertz being needed just for this amount of defined shape. Because again, 1, 3, 5, 7, and 9. So you've got all the way up to 9 gigahertz just to create this amount of a shape. Now, when you start playing with the applet, you'll notice that I can only pick lower frequencies. That's why it's important for me to help you to understand it's not necessarily the frequency that I pick that's important. So here I just picked 1024 hertz. And by default, it's going to show you the fundamental frequency in yellow. It's going to show you the third harmonic at the proper size. It's going to show you the fifth harmonic at the proper size in order to maintain that red square wave, that shape. With a soft attenuation curve, you can see that there is less ripple present, and the slew rate is even slower. So that's what you see here, is that if I take the third harmonic and reduce it by 20%, and the fifth harmonic and then I reduce it by 50%, notice how much softer this curve is. There's a little bit less ripple, but it's still a slow wave rising time. Now, if I feed this into a steep attenuation curve, applying a 3 dB cut to the third and a 6 dB cut to the fifth, notice that I've almost got my fundamental back. Now, the goal of this section was to help you to visualize the higher frequencies needed in the frequency domain in order to square off the shape in the time domain. Next, we're going to talk about the rise-fall time influence on the presence of these same kind of frequencies. Even in lower clock speeds, there are going to be higher order frequencies that can be of concern because it is the higher frequencies that create the sharp edge of a signal. It doesn't matter how long the cycle time is. If you want a sharp leading edge, you have to have high frequencies. That's one of the things that people don't understand when they're new into high-speed design, that it's a two-prong approach. It's high-frequency clocks, but it's also fast rise time signals, even on slow clocks. Now, if you're dealing with a slow signal, but you have fast edges, K is a good number to use in this equation. We're going to try and approximate what are these higher frequencies that you have to be concerned about. What I'm trying to show you here in this diagram, first of all, let's clarify. A rise time is typically defined to be between 10 and 90% of the entire change in voltage. It's called an 80% rule. So that's the time that I've got over here in this table. That's the time when you're going to be looking in your data sheet to try to determine what rise time they're talking about. That's the 80% rule. Now, over here in this table, what I've done is given you, based upon the ratio of K, the gentleman by the name of Rick Hartley, who also subscribes to using K equal 0.5. If we take 3 different signals with the rise time based upon this table, let's just pick 100. It's easier for math. Then notice over here, if we take the 100 picosecond and we divide that into 0.5, you end up with a high frequency of 5 gigahertz. Let me turn my pointer on, make it a little bit easier to see. Yeah. So you'll see 5 gigahertz is the highest frequency that you would be concerned with. Now, and it doesn't matter what the actual clock rate is that you're looking at. It's strictly based upon the rise time. If you're working with a really high frequency clock, then, or faster signals, light wave does this in general. Notice that I've given you a link here. They deal with 2832 gigabit per second serial data lines. They prefer to use 0.64. And if I use the same rise time, notice that my maximum frequency of concern jumps up to 6.4. So remember when we first started this, we said harmonic contribution and rise time are the 2 facets that we want to consider. So if I go back to the harmonic contribution that we want to look at, that uses the 5th rule that we were talking about before, where you had the fundamental 3rd and 5th harmonic. Now, if I take that same 100 picosecond signal and I apply that to this 80%, that basically says that 100% ends up being 125 picoseconds. And if I take 125 picoseconds here, 125 here, 125 here, 125 here is 1 clock cycle, then that would give me a fundamental frequency of 2 gigahertz. But with the 5th harmonic, means that I would have to be looking at 10 gigahertz as my total frequency, highest frequency of concern. So you can see comparatively that the rise time is definitely something to be concerned about. Not necessarily as important is if you have a really fast clock. So let's take a lower operating clock. Let's say it's 1 megahertz, but it has a really fast rise time of 100 picoseconds. Now this diagram will help you to understand that the need frequency is much greater than that 5th harmonic case, because if we did the 5th harmonic rule of 1 megahertz, you'd have 1 megahertz, 3 megahertz, 5 megahertz. 5 megahertz would be the highest frequency of concern. But when you look at the rise time aspect, you take that 0.5, which is what we said for our lower frequency signal, you divide it by that 100 picoseconds, you end up with 5 gigahertz. So a very low clock frequency can still have a very high speed concern. So polling question number 3. High-speed signals is a term reserved for what type of signals? Awesome. 93% of you all got all of the above. That's great. Now, I kind of threw in a little trick there when I talked about 125 picosecond fall time. We're going to address that in just a second here. But the correct answer is E, all of the above. Any digital signal, for that matter, and analog too, can have harmonic content. That content is going to consist of extra signals, that is frequencies, above the obvious working signal's frequency. So in the end, you have to ask yourself, what frequencies will I have to contend with in my design so you can know if there might be a problem? As we continue, the term high-speed signals will always refer to both types of signals. Polling question number 4. Now this one, I want you to pay attention to the wording in the question. What situation would you be more concerned about if this was your design? Okay. So I'm going to go through and explain the answers which one is correct and which one's not correct. But it looks like we got 26% got the correct answer, A. Now, for those of you who voted for D, all of them are equally concerning. Don't feel too bad. I kind of threw in a trick there because I said which one is the more concerning situation. If you didn't look at that, all of them are concerning, but not equally. So those of you who voted for A, you got the right answer. And the key is the 200 picosecond rise time. Because if we take 0.5, which we talked about as K, and we sub that into the equation, we come up with 2.5 gigahertz as our highest frequency of concern. The 16 megahertz clock for a microprocessor, which was B, again, because the working frequency is only 16 megahertz, the fifth harmonic would only be 48 megahertz, not very high. And because they're not typically squared off, then the rise time is going to be slower. So if we took it as the fastest, then 0.5 divided by 1 nanosecond would be 0.5 gigahertz. Again, definitely a concern, but not as much as the I squared C example. 240 megahertz differential USB 2 with a rise time of 325 picoseconds. Now, automatically, you might want to say, wow, that's pretty high frequency. That's true. But if you look at the fifth harmonic, again, you're not looking at nearly as high as 2.5 gigahertz. And if you, because it's a higher frequency signal, just to be safe, I picked 0.65. If we did that, that actually pushes that higher frequency of concern higher than it would with the 0.5. But still, it's only 2 gigahertz. Conclusion. When it comes to what is the highest frequency of concern in any circuit, you must consider the base frequency and the rise time taking place. Usually, rise times are pretty much the same as fall times, so the same rules would apply. Excuse me, I had a cough there. So number C, or letter C, it didn't matter whether it was a rise time or fall time. In the rare case of non-symmetry, you would take the rise or fall with the fastest slew rate. At the end of this analysis, you want to understand what high frequencies you're going to be dealing with, and why is that? When it comes down to it, again, go back to the FCC concept that we want to make sure that we don't have signals that are radiating out of the product that should not be there. Those radiations can take place from within or outside the product. I recently did a project with an RS-485 communication link using a MAX 3483 transceiver. The datasheet showed a test at 125 kilohertz, even though the part was able to go all the way up to 10 megabits, therefore a lot faster than 125 kilohertz. But the interesting thing, in the datasheet, they actually showed that when they ran the test at 125 kilohertz, notice all the high frequency content that was being generated by this part in order to keep this waveform nice and square. Now, true, 5 megahertz in this particular example is below the 30 megahertz that we'd be concerned about in the radiated FCC test. But the point is, when you look over here and they had slew rate control in it, they could actually tell the thing, I don't want you to turn on quite as fast or turn off quite as fast. Notice how they've reduced all this higher order harmonic. So when they're running at 10 megabits per second, they can make sure that they're going to have less energy being radiated on this twisted pair wire communication that we're going to be using. Next concept I'd like to discuss is called lumped versus distributed. Concerning radiated emissions, I want you to think in terms of the rise time compared to the conductor's length, aka the propagation time. If the rise time is much greater than the propagation time, then I want you to treat the path as a lumped component. What a lumped component is like an individual inductor, resistor, capacitor. If the rise time is significantly less than the propagation time, then you can look at the path as a transmission line, and hence it has distributed elements in it. Again, if you go back to the concept of what is a transmission line, you remember that we had distributed inductance and capacitance all along the line in equal increments. So it looked like as the wave was going through the transmission line, it was constantly seeing the same amount of inductance and capacitance in little individual sections, all the way going down the transmission line. And the key here is if you look at a transmission line in this situation, the greater the dV/dt, that is the change in voltage for a change in time, means that this node can be a greater voltage than this node because the slew rate is so fast. That creates problems. The key here is problems are going to arise the closer that your propagation time becomes greater than 1/4 of the rise time. Now, if you remember from some of your basic electronics, you'll recognize that time inverted is frequency, and you'll recognize that 1/4 is significant because antennas can act very well when you're talking about 1/4 of the wavelength due to that frequency that it's trying to transmit. That's where this comes from. So if you have a 1 nanosecond rise time, then you want the conductor length to stay under 250 picoseconds. Your greatest probability of radiating a signal is once that conductor length gets above that rise time. Once a path becomes distributed, it is more likely to have reflections, ringing, and crosstalk. Here's the key statement I want you to kind of burn in your brain. If there's a high dV/dt that's created over a significant distance, then that's going to create radiating pulses, guarantee you. Now, if you notice on this diagram, I have a picture of an antenna. When you have a distribution of charges, in other words, a large dV/dt, then one end of the antenna is going to have a very positive nature, and the other end is going to be a very negative nature. That creates this distribution of an electric field radiating like this. But at the same time, because you have a fast slew rate, you're going to have a lot of current trying to move through this inductor. The current going through the conductor creates your magnetic field. So the magnetic field being radiated at the same time as the electric field creates this concept of a TEM wave, or transverse electromagnetic wave, because the E field and the B field are orthogonal or perpendicular to each other. And when that happens, this is what you get to see. These fields radiate out. And that's what the FCC test is looking for, is it's going to measure this electric field at a fixed distance away from that track that's on your PCB that's acting like an antenna. Now, let's talk about a distributed example. Now, in air, dielectric constant, or the relative permittivity, is 1. The propagation time, 84.75 picoseconds per inch. In a microstrip, which most of you all are probably familiar with, this is a transmission line built on FR4, very common dielectric, and its permittivity, or dielectric constant, typically 4.5. The propagation time is going to be increased by a velocity factor. Now, without getting complicated, let me give you a real life scenario. So imagine yourself in a hallway, and you're running down the hallway, and all of a sudden you notice that there's a 2-foot thick piece of Jell-O, and you're going to have to run through this wall of Jell-O. Well, you know as well as I do, when you hit that Jell-O, you're going to slow down. When you get through the Jell-O, you're going to speed back up. Well, it's the same thing with a wave. If a wave is traveling through air and it's in this transmission line, has to go 2 inches or 2 feet, and then it comes out the other end in air again, it's going to slow down by this velocity factor while it's in the dielectric material. Now, we're going to assume that the microstrip has an effective dielectric constant of 4. The reason why it's 4, not 4.5, is because some of the wave, as we've covered in before, is going to actually travel in the air and not completely embedded in the dielectric. So if we use that effective dielectric constant, then the new propagation time is 169.5 picoseconds, because it's basically halved the speed. Now, if we revisit our previous example where we talked about a 1 nanosecond rise time, implying that our propagation had to be less than a quarter nanosecond, or 250 nanoseconds, then if you divide that 250 by the 169.5, you get a length limit of 1.47 inches. Now, if you're familiar with a wave propagating through air travels about 12 inches in a nanosecond. Well, that means that if I want it to be less than a quarter inch, I would normally in air want a device that's only 4 inches long. But in a dielectric constant, that's going to slow the wave by half. Then instead of 12 inches in a nanosecond, it's only 6 inches in a nanosecond, which a quarter wave would then be 2 inches, or I'm sorry, 1.5 inches. So again, this mathematically makes sense. We're going to try and stay away from quarter wave antennas. Now, there are other concerns. Because high frequencies have short wavelengths, then high-speed signals are more likely to create other problems even within your own product. The closer a trace length is to a wavelength, the more likely it is able to radiate. Even if the whole signal is not coupled, the high-frequency component would be. That means the leading edge is going to create a pulse on a track next to it. If you have a receiver, if you have all these other signals, it's going to be a problem because a receiver depends on this front end being quiet so they can hear faint signals. This is referred to a low noise floor. If you got all this other trash running around, these pulses coming around from other high-speed signals, what that's going to do is it's going to raise that noise floor and reduce the receiver's ability to listen. In summation, high-speed signals refer to any signal where there is significant high-frequency content, regardless whether it is from the operational base frequency or from fast switching speeds. And as far as the FCC is concerned, anything radiated above 30 megahertz is a concern in air. Routing will make a major impact on the radiation of any high-speed signal you have in your product. Understanding the impact of fast switching speeds is critical to realizing just how much attenuation needs to be made to the PCB layout. Now, we talked about an example of the quarter-inch wavelength. So if you have a lot of signals that have a fast rise times, you're going to have to keep track of them all and make sure that these tracks don't exceed a certain length for each one of the situations. So I'd like to go to polling question number 5, please. And that is, how would you rate the material presentation today? All right, thank you very much for that feedback. Let's see, 5 and 8. Okay. And one more question, polling question number 6. If I were to teach this class again, or this webinar again, I really would appreciate your input on what areas would you think I need to spend more time on to help you have a better understanding of the overall picture? Or do you think that the balance was fine? All right, looks like critical length and lumped versus distributed were pretty high on the list. Thank you again for that input, and I appreciate you being here today.
Sean, thank you very much for your presentation there. It was